Hello, and welcome to our discussion of Liouville's theorem. Liouville's theorem says the following: there are no bounded non-constant entire functions. So what does this mean? Suppose you have a function f that is entire and bounded. So to be entire, that means f has to be defined on the whole complex plane and also holomorphic on the whole complex plane, or as we are now saying, analytic on the whole plane. And f is bounded. There is a number m greater than 0, such that the modulus of f of z is less than or equal to m for all numbers z in the complex plane. If that is the case for f, then Liouville's theorem requires the following to hold for f. There must be a single number c in the complex plane, such that f of z is equal to c for all complex numbers z. So there are no bounded non-constant functions that are differentiable on the whole complex plane. And this is wholly unlike what we know from the real case. If you take f of x equal to sine of x, or g of x equal to e to the minus x squared, these are real analytic functions. They're not just infinitely differentiable. They can also be expressed as power series on the real line. And they're bounded functions. Specifically, you could take m equal to 1 in the estimate above. But Liouville's theorem says that a function like z goes to sine of z or z goes to e to the minus c squared must be unbounded on the complex plane, because neither of these functions is constant and both are entire. This is a really strange feature of complex differentiable functions when those functions are defined on the entire plane. To prove Liouville's theorem, we will need a little lemma that we'll call the Cauchy estimates. So say that f is analytic on a domain D, and you have a point z0 in D, such that the closed ball of radius r centered at z0 is contained in D. Then the following estimate holds. The modulus of the kth derivative of f, evaluated at this point z0, is less than or equal to k factorial divided by r to the k, times the maximum of the modulus of f of z, where z can satisfy modulus of z minus z0 is equal to r. So we have a bound on the kth derivative of f at z0 that depends on the number k, that depends on the radius of this closed ball, and that depends on the values of f taken around the boundary of the ball, the circle of radius r centered at z0. So you will prove this lemma, these Cauchy estimates, in an exercise. We'll use the lemma as follows. Here's our proof of Liouville's theorem. We want to show that f is constant. And that's the same thing as saying that f prime of z is equal to 0 for all z. So let's use the Cauchy estimates to control this first derivative, f prime. And in particular, we'll use the Cauchy estimates for an arbitrary number r, because f is entire, so f is going to be holomorphic on every ball centered at z of radius r. And so we get the modulus of f prime of z is less than or equal to 1 divided by r times the maximum of the moduli of f of c, where modulus of c minus z is equal to r. Now, what do we know about the modulus of f of c for some complex number? We're assuming in the hypotheses of Liouville's theorem that f is bounded. So the modulus of f of c is always less than or equal to m, regardless of what c is. So we get modulus of f prime of z is less than or equal to m divided by r. And this number m doesn't depend on r. So now we can use the squeeze theorem. We know that 0 is going to be less than or equal to the limit as r goes to infinity of the modulus of f prime of z, which will be less than or equal to the limit as r goes to infinity of m divided by r. Everything in this chain of inequalities, because it's an inequality, is a real number, specifically a non-negative real number. Now, of course, this limit on the modulus of f prime of z is independent of r, and what happens to this limit as r goes to infinity of m divided by r? That is equal to 0. And so we get that the modulus of f prime of z is equal to 0, but we also know the modulus of a complex number is equal to 0 if and only if that complex number is 0. So f prime of z is equal to 0, where z was an arbitrary complex number, and so f must be constant.